I also thank you, Professor Angaro.
Thank you.
Good evening, everyone. Today I will talk about our ongoing research work titled as Energy Saving Membrane-Based Desalination Hybrid Process for Zero Liquid Discharge in Qafco plant. Qafco plants are known for their high production of ammonia and urea around the world. However, currently they're facing major issue of wastewater or processed water stream generated from their process unit. To tackle this issue, we can use a conventional thermal distillation process to resolve this issue. However, these processes are known for their high consumption of energy. As an alternative, we can use direct contact membrane distillation process as we propose here. So what is DCMD? DCMD system or process is based on thermal gradient created across a microporous hydrophobic membrane that allow water vapor molecule move from the hot side to the cold side where the permeate is collected. The advantages of this system basically on its simplest configuration as well as the low grade energy requirement, or we can use here a renewable source of energy. However, this system suffer from or the drawbacks of this system is based on the membrane wetting issue or temperature polarization effect. Here in this work, we will focus on demonstrating DCMD system along with the crystallizer unit to solidify all the wastewater uh, stream and in order to attain a zero liquid discharge. And to tackle wetting issue, membrane wetting issue, we will work on fabrication of superhydrophobic membrane. Moving to the experimental section, here is our DCMD experimental setup. As you can see, here is DCMD test cell where we place our uh, membrane. And after we perform the DCMD process, the external crystallizer unit, we use here rotatory evaporator to crystallize the supersaturated rejected water. And for the fabrication of the membrane, we use an electrospinning technique. Moving to result and discussion part, the DCMD system were tested using assimilated wastewater along with the commercial membrane, MD membrane, and we only tested the effect of the feed concentration, and we kept the other operating variable constant. We noticed that at high salinity, the system was able to exhibit high water recovery as well as high about 99% rejection, salt rejection. And the SEM images confirmed that no scaling of fouling was observed with the consequence run of the MD system. After we run the MD process, we fed the supersaturated wastewater to crystallizer unit, and we were able to collect different amount of solid crystal. The different amount is based on the initial concentration of feed solution. The highly initial, the more solid collected. Moving to the MD fabrication section, we were able to confirm that what we have made, it is hydrophobic membrane since the contact angle were greater than 100 degree, and a nanofiber confirmed by the SEM image and with stable mechanical and chemical properties. Finally, at this stage, we were able to reject 99% of salt and recover 22% of water, pure water, using assimilated wastewater and operating at 70-degree temperature. So in future work, we are planning to study a different operating variable effect, as well as test the system using actual wastewater. As for the fabricated membrane, we want to improve its hydrophobicity to be greater than 150. Thank you for your listening.
Hello everyone, I am Dr. Amol Mane from India presenting the poster in online conference on emerging and enabling materials organized by Center of Advanced Material, Springer's Emergent Materials Journal, Qatar University and Texas A&M University at Qatar. The title of my poster presentation is PD V25 nanorods based gas sensor technology for industrial use and environmental protection. In the present work, vanadium pentoxide nanorods have been successfully deposited onto the glass substrate using simple and cost-effective chemical spray pyrolysis deposition technique at optimized substrate temperature of 400 degrees Celsius. Further, PD sensitized V25 nanorods have been successfully synthesized using simple dip and dry method. The prepared thin films are then characterized by different characterization techniques such as X-ray diffraction, field emission scanning electron microscopy, and energy dispersive X-ray analysis. Further, these films are used for gas sensing for its use in industrial application and environmental gas detection. In the present discussion, in the result and discussion part, the X-ray diffraction analysis shows the formation of orthorhombic crystal structure of V25 nanorods. The field emission scanning electron microscopy micrograph show the formation of nanorods like morphology, which provides high surface area to volume ratio for gas absorption. The nanorods are densely grown with uniform length and similar shape. The small pores of varying sizes are also observed due to random orientation of nanorods over the surface of film, which provides larger contact area for gas adsorption and thereby more adsorption sites for gas adsorption. The presence of palladium in the PD sensitized V25 nanorods is confirmed using energy dispersive X-ray analysis study. Generally, the gas sensors for practical applications have required not only strong response but also have good selectivity towards the target gas. So to investigate the selectivity of PD sensitizer V25 nanorods, the response to various gases such as ammonia, NH3, H2S, carbon monoxide, carbon dioxide, sulfur dioxide, and nitrogen dioxides are examined. The selective coefficient study shows that PD sensitized V25 nanorods are more sensitive and selective towards NO2 gas. This is due to higher electron affinity of nitrogen dioxide gas, that is the 2.28 electron hole around, in comparison with pre-adsorbed oxygen having electron affinity around 0.43 electron volt. In nitrogen dioxide, nitrogen contains one unpaired electron. After forming the covalent bond between nitrogen and oxygen, this unpaired electron in nitrogen is the reason why chemi absorption of nitrogen dioxide gas is more likely in comparison of other gases. This unpaired electron in nitrogen of NO2 forms bond with the surface oxygen of PD sensitized V25 nanorods and subsequently promote the chemi absorption. The V25 nanorods show highest response of 41% at optimized substrate temperature of operating temperature around 200 degrees Celsius for 100 ppm NO2 gas with response and recovery times of 20 seconds and 150 seconds respectively. Whereas the PD sensitized V25 nanorods, the enhanced NO2 gas response of 75% is observed at an operating temperature of 200 degrees Celsius for 100 ppm NO2 gas concentration with response recovery times of around 22 seconds and 126 seconds respectively. The enhancement in gas response for PD sensitized V2 nanorods is attributed to the combined effect of electronic and chemical sensitization mechanisms. The response and recovery times are found to be increased with increasing NO2 gas concentration from 5 ppm to 100 ppm. the detection and monitoring of hazardous gases. Below the exposure limit is important in different fields such as industrial emission control, vehicle emission control, household security, and environmental monitoring. So in the present work, the lower NO2 gas concentration detected by PD sensitized V25 nanorods is found to be 5 ppm, which is 2 times lower than the immediately dangerous to health and life value. Thus, in conclusion, the higher response selectivity and fast response recovery times of PD sensitized V25 nanorods based sensor towards NO2 gas has potential application for development of advanced sensing devices. In addition, we can say that nanorods like morphology of V25 with high surface area to volume ratio can open the novel scientific, environmental, and technological applications in various fields such as supercapacitor electrodes, optoelectronic devices, portable electronics, and aeronautical devices. Thank you for your kind attention.
My name is Sarah Ayad Ahmed. I am a postdoc working with Dr. Khalid Youssef from the Materials Science and Technology Program at Qatar University. The title of the research I'm presenting today is In situ growth of single crystal plasmonic aluminum lithium graphene hexagonal nanoplatelets using ball milling. Now, metal nanoparticles with anisotropic shapes are known for their unique localized surface plasmon resonances, which result in concentrating strong electromagnetic fields directly around the metallic nanoparticle during its interaction with light or an electromagnetic wave. Now, the significance of this unique optical behavior lies in the tremendous potential for its cutting-edge applications, such as plasmonic enhanced photovoltaics, photocatalysis, sensing, and bioimaging, to name a few. Now, research has primarily focused on the synthesis of gold and silver nanoparticles because of their relative ease of synthesis. However, these metals, they have limitations, including their high cost. Recently, aluminum has gained a significant interest as a promising practical alternative to the coinage metals gold and silver. And this is because it is far more abundant, it has a lower cost, and most importantly, it has a higher density of free electrons, which means a higher plasmon frequency and a better optical performance. However, the problem faced with aluminum is its high reactivity, which renders the synthesis of aluminum nanoparticles using the well-established, well-developed chemical synthesis techniques challenging. So the objective of this research was to synthesize plasmonic anisotropic aluminum-based nanoparticles using a purely mechanical technique to avoid the problem of aluminum's high reactivity. Now, in this study, the synthesis technique of choice was ball milling because of its simplicity and capability or ability to produce nanomaterials. Now, the secret to growing single crystal nanoparticles using what is otherwise known as a top-down severe plastic deformation technique, such as ball milling, lies in the careful design of the system constituents. That is to add specific element, each of which will play a certain role in growing those single crystals. And so in addition to aluminum, we added certain amounts of lithium and graphene nanoplates, mixed them all together in a simple one-step ball milling synthesis procedure. Now, the specific role of each of these elements will become apparent and more clear in the discussion section. As we see in the upper right corner of the poster in the SEM image, particles with perfect hexagonal platelet-like morphology and well-defined facets are distributed throughout the sample. Now, TEM analysis and the despacing measurements and the 6-fold symmetry from the corresponding selected area electron diffraction pattern all confirm that these hexagonal nanoplatelets are indeed aluminum single crystals that have 111 facets, atomic planes, or 111 facets. In addition, the TEM elemental mapping confirmed the homogeneous distribution and the coexistence of both aluminum and carbon in the hexagonal nanoplatelets. The UV visible spectrum, also shown in the poster of the hexagonal nanoplatelets, confirmed the plasmonic nature of the synthesized nanoparticles, where they exhibited a high plasmonic absorbance resonance peak in the UV region. Now, the significance in this study is that the growth of these single crystal nanoparticles was achieved using a purely mechanical technique. No state-of-the-art bottom-up techniques were used to grow the single crystals. We absolutely did not use any kind of surfactants or chemicals or reducing agents, which are otherwise used to control the single crystal nucleation and growth. So how did these single crystals or nanoparticles form? In general, single crystal formation happens in two steps, nucleation and growth. The single crystal formation first requires a nucleus or a template or a substrate on which the crystal growth is initiated and directed. Now, during milling, the aluminum particles or atoms are forced into contact with the graphene nanoplates. However, the initial incompatibility between graphene and HCP graphene and FCC aluminum generates lots of stresses at the interface. And so the aluminum is forced to rearrange and diffuse in order to reduce this lattice misfit and creates or rearrange itself in the 111 plane, the 111 direction on the 0002 graphene, and we end up with this arrangement at the interfacial interaction. Now, the growth of the hexagonal nanoplatelets is then supported by the context of the Gibbs-Wolf theorem, which suggests that for an FCC nanoparticle, you need to maximize the 111 expressions or platelets or planes in order to reduce the total surface energy. And so you end up with a three-dimensional tetrahedral or octahedral nanoparticle. However, even though, yes, our TM investigations prove that our hexagonal nanoplatelets have 111 facets, they are rather two-dimensional and hexagonal in shape rather than three-dimensional and tetrahedral or octahedral in shape. And so here comes the role of lithium. Lithium has been experimentally proven to reduce the stacking fault energy of aluminum, which means it introduces planar defects such as stacking force or twinning planes into the aluminum lattice, forcing the crystal growth to happen in a two-dimensional planar form. And so we end up with hexagonal platelets rather than three-dimensional nanoparticles. Now, in conclusion, it is said that crystals are like people. It's the defects in them which tend to make them interesting. And indeed, in the study, we were able to synthesize for the first time aluminum-based nanoparticle using a mechanical technique by manipulating the structural defects induced by milling and by the presence of both lithium and graphene nanoplates in aluminum. Thank you.
A very good day. Myself, Kuku Thomas. I'm going to discuss with the topic synthesis and photoluminescent studies of host-sensitized dysprosium-doped zinc tungstate nanophosphor. Rare earth doped inorganic materials have attracted a significant amount of attention due to their potential applications in the field of display devices. So, here, a systematic and elaborated investigation on the structural and optical properties of dysprosium-doped zinc tungstate nanophosphor was carried out. So first of all, a phosphor is a substance which exhibits the phenomenon of, and a phosphor generally consists of a host material and an activator. And these activators which are primarily responsible for the photoluminescence properties. And here we choose the host is the zinc tungstate and the activator is the dysprosium. The dy3+, it is trivalent dysprosium has a great of applications in the field of display devices. So the dy3+ is chosen as the activator and the zinc tungstate is the host material. So the dysprosium is a rare earth element, belongs to the lanthanide series, and the dysprosium acts as an activator for many host materials for making potential nanophosphors. So next we moving on to the synthesis technique. The pure zinc tungstate and dysprosium-doped zinc tungstate nanophosphor is prepared through a very simple chemical co-precipitation method. And in this method, we take the reagents used are the zinc nitrate, sodium tungstate and dysprosium nitrate pentahydrate. Here the stoichiometric measure of the reagents are dissolved in deionized water and they are allowed to magnetic stirring for 1 hour and then they dry heat at 90 degrees Celsius for 12 hours and the prepared sample is then annealed at 650 degrees Celsius for 5 hours. The resulting sample is grinded in a mortar jar for getting the desired nano powder. And this nano powder is then allowed to different characterization techniques. First one is the structural characterization. For structural characterization, we take the XRD pattern. Here we got the well-defined diffraction peaks. This well-defined diffraction peaks suggest the highly crystalline nature of the zinc tungstate. And also, according to JCPDS file data, the prepared sample belongs to the space group P2 bar C of 13 And also we got the phase of the zinc tungsten, it is pure monoclinic phase. And also the Scherer formula, using Scherer formula, the crystallite size of the pure zinc tungstate can be determined and is found to be 27.188 nanometer. And the doping of dysprosium does not alter the structure. So we can conclude the fact that the dysprosium is incorporated well into the host matrix. And next is the optical characterization techniques. The optical characterization techniques, we take the excitation and emission spectra of both pure zinc tungstate and dysprosium doped zinc tungstate. And from the emission spectra of the pure zinc tungstate indicates that our host matrix is self-luminescent character. So we got the emission spectra. And in case of the dysprosium doped zinc tungstate, there is for the excitation spectra, there is an intense charge transfer band. And the dysprosium peaks are very less feeble compared with the charge transfer band. So we take the host excitation for the emission spectra in the case of dysprosium doped zinc tungsten nanophosphor. So we got a broad blue region along with the sharp lines, and this sharp lines indicates the dysprosium. Here we got the strong emission is the yellow one. So this corresponds to the electric dipole transition, which is indicates that the asymmetrical nature of dysprosium in host matrix. And this sharp lines concludes that an efficient energy transfer takes place from the tungstate to the tungsten to the dysprosium ions. At some levels of the dysprosium and the tungsten, some levels are matched with each other, so that an efficient energy transfer takes place in between them. And so we got the dysprosium ions, the sharp lines in the emission spectra. And from the CI chromaticity analysis, we got the coordinates which corresponds to the white region. So the prepared sample is called the cool white region, and the color purity of the sample is very low. It is 17.8%, which is very low. So the emission is white light. So we got the conclusions that our prepared sample is prepared through synthesized through chemical co-precipitation method. We take the structural and photoluminescence properties, and from structural characterization we got the phase and the crystallite size of the zinc tungstate. And from the emission spectra we got the fact that the host matrix is self-luminescent character 1. So we got the emission spectra, and also we got the fact that our prepared sample is a good candidate for phosphor converted white light emitting applications. So thank you.
Hello, good day. It's my pleasure to be part of this conference. Here I would like to discuss about my current work on lithium recovery using energy efficient lithium alumina electrodes. So first of all, I would like to take your attention towards why lithium, why this research is important. Lithium is widely used in industrial scale, widely used element nowadays because of its widespread use in portable electronic devices, in mobile phones, electronic cars, and all that. So 65% of its uses in energy storage appliances. Currently, lithium is extracted from concentrating salt lake brines. Salt lake brines have lithium concentration of from about 100 to 1000 ppm. So what they do is they do solar drying of the salt lake brine until the concentration of the concentrated brine is at a given desired amount suitable for precipitation, and then collection of lithium in salt from. So, but this solar drying process takes time, and it's not the same every time. It can be varying from somewhere from months to years depending on climatic changes. Also, the quality of lithium concentrate is not the same. You can't compare batch to batch because of this inconsistent nature of sunlight and also other climatic conditions that is unknowingly influencing it. So in our research, we plan to replace solar drying process and also the salt lake brine. You know, salt lake brine is not the only resource, only lithium rich resource. There are some minerals, geothermal brine, salt lake, but salt lake is the widely used one. And also salt lake brines are geographically confined. It's not spread it evenly all around the world. It's only confined to several locations. So if we can use another resource that's rich in lithium, and you can find everywhere, then the extraction of lithium is going to be even easier. So here our proposal is to use seawater reverse osmosis brine. Reverse osmosis plants are operating worldwide in almost all countries, and not one, many, multiple of them. And depending on its efficiency and which pass reverse osmosis is used to get produced water, and in the sideline we are getting a lot of this brine or the RO reject to deal with. Depending on the pass, the concentration is different. If you consider first pass RO reject after first pass, if the plant is operating at 50% efficiency, we double the concentration of lithium. In seawater, the lithium amount is massive, but the concentration it's very low, lying only at 0.12 ppm. So even though it's huge, it goes to a waste, cannot use. So in this regard, we propose the using of seawater reverse osmosis brine as the lithium-rich resource with electrochemically switched ion exchange technique. So why this technique is because if you compare it with ED and CDI, the other electrochemical techniques, the resource recovery is higher in E6 as well as specific energy consumption is much lower. And why these lithium alumina electrodes? Mostly lithium manganese and lithium iron phosphate electrodes are used in this intercalation, de-intercalation electrodes used in this E6 principle. But if we can get rid of this manganese, iron and phosphate parts from our electrode, that's going to be more environmentally sustainable. There have been computational studies saying this works better, but not experimentally tested so far. So this is going to be the first research in that aspect. So here we use hydrothermal technique to synthesize lithium alumina material, and XRD graphs here says it got after annealing we got the phase lithium alumina phase that we want in the gamma phase, and the material looks homogeneous and uniformly sized cube shaped lithium alumina. And we did charging and discharging and charging for capture and release of this material because it works in intercalation and de-intercalation. At first we have to do an activation step to make this catalyst delithiated so that lithium in our resource can get into the voids of the catalyst, the electrode material. So we studied several parameters, and out of them current density was found to be the most influencing parameter for the specific energy consumption and also the recovery rate. We found 0.2 milliamperes per square centimeter to be the best. And here you can see the capacity versus voltage curve. Area under the curve gives us a specific energy consumption. So we found this our material can produce lithium alumina in higher resource recovery rate of 97% purity with lower specific energy consumption. Therefore, we are very happy to say that we are successful in demonstrating the prospects of greener concentration of lithium using lithium alumina material. Thank you very much for your attention. Again, it's my pleasure to be part of this conference. Thank you.
Good morning, everyone. I am Sari Shabir. I am the PhD student in College of Engineering, Qatar University, and I'm also working as a research assistant at Center for Advanced Materials in Qatar University. Today, the topic of my poster presentation is self-healing performance of polymeric nanocomposite coatings, modified with zirconium oxide nanoparticles. So, starting from the background, like what was the motivation behind this work? So, as we all know that corrosion has been proclaimed as one of the most destructive phenomena, which not only results in the economic loss, but also life-threatening. So, and it can cause massive economic environmental problems. So Qatar being a humid country, especially in the oil and gas field, the pipelines experience a lot of corrosion because of humidity and the change of external factors, especially at offshore and onshore. It has been estimated that more than 70% of the cost has been spent on the maintenance of these pipelines in oil and gas industry. So there are different modification techniques which can be utilized to protect the metal or the steel substrate from the external environment or to get the interaction with the external environment. They involve the thick coatings, thin coatings, plasma techniques, electrodeposition techniques, or the polymeric coatings. Basically, the utilization of polymeric coatings is the most advanced approach to protect the steel from the destructive corrosive phenomena. Polymeric coatings not only provide the physical barrier between the metal with external environment, but also they provide the barrier with the oxygen, with the water, which can comes from the external environment, and it can also act as a matrix to accommodate the functional species. So the corrosion protection mechanism basically involves the formation of the passive layer on the metal surface, which can protect the metal from the outer environment. Metal surface from the outer environment, and the functional species. The functional species that are being loaded into the matrix basically comes out of their carriers, and they protect the steel from the from any change in the external factor. What is done in this work is basically we utilize the zirconia oxide nanoparticles with the corrosion inhibitor and the self-healing agent, and we loaded this into the zirconia oxide nanoparticles, and a scratch was made, and these loaded zirconia oxide nanoparticles are reinforced into the polymeric matrix. Epoxy was used in this case as a polymeric matrix, and after we loading reinforcing the epoxy with the zirconia oxide nanoparticle, modified zirconia oxide nanoparticles, they are being deposited on the steel substrate, and a scratch was made. Manual scratch was made with a scalpel. And this scratch acts as a mechanical force to release the functional species from the zirconia oxide nanoparticles, and they form the passive layer over the on the defect area that was a scratch, and protect the metal from the from any propagation of the corrosion activity. The mechanism behind this was due to the formation of the scratch, the corrosion inhibitor comes out of the nano container. And the self-healing agent was also come out of the nano container. And after they came out of the nano container, they formed the passive layer due to its localized change in the pH at the defect area. How these coating was deposited? The pre-coating was the epoxy coating modified with zirconia oxide nanoparticles with a corrosion inhibitor, and the top coat was the epoxy coating modified with the self-healing agent. So it was the double layer coatings on the steel substrate, which were providing the double action of inhibition and self-healing. This part is just showing that how loading was done on the zirconia oxide in the zirconia oxide nanoparticles. That was vacuum assisted loading of corrosion inhibitor and self-healing agent in the zirconia oxide nanoparticles. Different characterization techniques was utilized to endorse the successful loading of the functional species into the zirconia oxide nanoparticles. This is a SEM analysis which is showing the spherical morphology of the nanoparticles, and it is also showing that after loading the morphology has not been changed, so it doesn't affect the morphology of the nanoparticles. However, the EDX analysis was done to confirm the presence of functional species into the zirconia oxide, and EDX analysis confirmed that the main components of the functional species has been present into the zirconia oxide nanoparticles. The further characterization techniques involve FTIR analysis, TJ analysis, UV analysis, BT analysis, and FTIR analysis was done to confirm the chemical bonding and the interaction that has been taken place before and after loading of the zirconia oxide nanoparticles, and it has been seen from the FTIR analysis that the main peaks of the imidazole and PEI has been seen into the zirconia oxide nanoparticles with the main peaks of zirconia oxide nanoparticles. The BT analysis was done to study the specific surface area and the pore volume before and after loading, and it is the rule that after and before loading, the pore surface area should be reduced. Specific surface area and the pore volume should be reduced after loading. So this graph is showing the successful loading because the pore volume and the specific surface area has been decreased after loading. This figure 3 is the TG analysis, which also confirms the loading because before loading the TG analysis, the thermogrammetric analysis was done to study their thermal stability at different temperature. So zirconia oxide nanoparticles is highly thermal because even after 800 degrees centigrade, there is no degradation in the nanoparticles. However, after we loaded into the imidazole and PEI, it has been seen that it is showing the major degradation peak at the melting points of the imidazole and the PEI. But however, after this point, there is no degradation because of the high stability of the zirconia oxide nanoparticles. The UV analysis was done to study the pH sensitivity of the nanoparticles. It has been seen that the release of the particles is sensitive to the temperature, is sensitive to the pH values and the different times. The pH values that we selected was pH 2 acidic and the basic, that was 2, 5, 7, 9 and 11, and the time we selected was 24, 48, 72 and 96 hours. So with the passage of time, we have seen the decrease in the in the release of the functional species because of the decrease in the concentration of the species. However, the release is more pronounced in the acidic medium as compared to the basic medium. So imidazole and PEI are more effective in release from the nano containers in the basic acidic medium. SAM analysis was done to study the self-healing process in the coatings. For this purpose, the coatings has been made on the has been deposited on the steel substrate, and the scratch was made over it. And as soon as the scratch was made, we have seen that at the day 1, the scratch width was almost 116 nanometer. But with the passage of time, it can be seen that the width of the scratch has been decreasing due to the formation of the passive layer on the steel on the scratch area, because when the scratch was made, the localized pH has been changed, and the polymer, which was the self-healing agent, start to oxidize from the when they interact with oxygen, and it formed the passive layer on the scratch area. And the scratch area, the EDS analysis of the scratch area has also been done, which confirms the presence of the self-healing, the main components of the self-healing agent and the corrosion inhibitor. The main testing involved for these coatings was to study the corrosion inhibition via electrochemical impedance spectroscopic analysis was done to study the corrosion inhibition behavior of the blank epoxy coatings. 4 different types of the coatings has been made for this purpose. Blank coatings, the blank epoxy coating, the epoxy coatings with the zirconia oxide and imidazole, epoxy coating with zirconia oxide and PEI, and then a double layer of the epoxy coatings. So from the result that has been obtained shows that with the passage of the time, the blank epoxy coating starts to deteriorate because these coatings were blank and there were no chemical species present inside these coatings which can protect them from the corrosion propagation, and also due to the formation of the conductive path into the coatings, this leads to the water starts to move into the coatings and corrosion starts to propagate. And because these coatings are they have more pores, and the motivation behind adding the nanoparticles into the coating is to reduce the pores, because it increases the strength of the matrix. So when the epoxy coating has been loaded with the functional species, we have seen that the corrosion inhibition performance has been increased, and the coating which are being the steel substrate which are being coated with the double layers, that is pre and top layer, has shown the high values of impedance with the passage of time. So it's a proof that the coatings are providing an excellent barrier to the steel substrate from the external environment. And when the graph was drawn between the pore resistance and the charge transfer resistance, also showing the same results, because that for the epoxy coatings, the resistance has been decreasing, and for the rest of the coatings, the resistance has been increasing. So these are the equivalent circuits which we use to fit the data, for the coatings which is been modified with epoxy and nanocomposite coatings. So these coatings the conclusion of our work is that the epoxy-based coatings are the target high scientific, economic, social, and environmental impact, and they can not only use in the oil and gas field, but however they can also be used in many other industries, infrastructures, water transportation, renewable energy, and they have a lot of scope in the future. Not only epoxies but other polymeric matrix. Which are being reinforced with the different smart containers. They have the lot of scope in the future for the protection in oil and gas or other industrial applications. So at the end, I would like to thank Qatar Foundation for funding this project, and Qatar University and Center for Advanced Material for providing us the opportunity to work over this project and to present my work. And this work is also been published. I've also added the reference of this work. And thank you so much. And thank you for providing me the opportunity to share my work. Thank you.
Good morning. I am Dr. Sanu Matthew Simon from Marthoma College, Tiruvalla, Kerala. Today I'm going to present before you the poster entitled Interplay Between Porosity and Wetting Behavior for Polymer Modified Titanium Zirconia Composites. Titanium, as we know, it's very applicable in self-cleaning surface for day-to-day life. Incorporating zirconia into the titanium will enhance the band gap, and it will also prevent the electron hole recombination, which will enhance the self-cleaning property. Polymer modification of titanium zirconia composites will increases the surface roughnesses, which will allow the retainability of the composite films. Today we have going to present before a film two types of films, which on the basis of titanium zirconia and with the polymer modification, with how high transmittance and also with the thickness, high range of thickness. Our aim is to develop thick superhydrophilic coatings which are very transparent, and we are also trying to prepare the films on the micrometer scale. And we are using here the technique sol-gel assisted dip coating method for the preparation of these films. Here we have prepared two films. First one is based on PMMA alone with the titanium zirconia, and the second one is PMMA and pluronic F127 combination with the titanium zirconia. Pluronic F127 is a copolymer, the triblock copolymer. For the analysis of the films, we have carried out elemental mapping using ADAF imaging. In the ADAF imaging, we can see that the both titanium and zirconia presence throughout the surface of the films, and titanium zirconia is homogeneously seen throughout the surface, and is clearly confirmation the presence of the elements over the surfaces. For the morphological studies, we have carried out the FISM analysis. For the PMMA alone sample, that's a figure B, we can see that it is very well clear, well smooth surface is observed for the PMMA alone sample. But we have incorporated pluronic F100, so we can see small porous structure over the film, which means the surface roughness is increased due to the incorporation of pluronic F107. We have also checked the cross-sectional imaging of the film also. We can see that cross-sectional imaging, we can see for both films, it is in the range of 2.6 micrometer. That means the films are very highly thick films. The self-cleaning property is measured on the basis of contact angle. For the contact angle, for both films, we have checked out. First, we have the PMMA alone. PMMA alone samples, we can see the contact angle is 92 degree. For the PMMA and the pluronic F107 sample, the freshly prepared films, we have the contact angle is 57 degree. For 3 hours radiation, UV radiation, we can see that the contact angle is reduced to 29 degree. And for the PMMA and pluronic F107 film, it is decreased to 90 degree respectively. And also for 6 hours, it can see that further decreased to 25 and 10 degrees respectively. That means it reaches to range of superhydrophilic nature for the PMMA and pluronic F107 film. We have also carried out the retainability of the film. So after 24 hours, what happens to the contact angle is checked out. We can see that 25 degree is increased to 32 degree for the PMMA alone films, whereas the contact angle is increased only to 11 degree for the film of the case of PMMA and pluronic F107. Now, this means that this is the superhydrophilic nature of the PMMA and pluronic F107 is highly retainable in these films. For the checking the mechanism, we have carried out 3D Raman imaging. And for the 3D Raman imaging, we have carried out the compare the polymer, titanium, and zirconia Raman imaging separate is carried out. We can take the both of the polymers is thoroughly homogeneous distributed throughout the surfaces, whereas the TiO2 particles and ZR2 for the PMMA alone structure is concentrated only for a particular region, whereas in the case of PMMA and pluronic F187 films, we can see that it is throughoutly distributed throughout the surface, which is agreement with the elemental mapping also. And thus we can concluded the mechanism behind the titanium zirconic films. We have two types of mechanisms. That means we have a photo-induced superhydrophilicity is observed here. First, we have TiO2 presence of the TiO2 presence will degrade TiO2 ions. TiO2 ions will degrade the dot due to the presence of electrons at O2 minus molecules, O2 minus ions, and this will degrade the dot and removes into the small molecules, and which the sheeting of the water due to the hydrophilic nature will cleans out the surfaces. This is clearly observed from the photo degradation of the methylene blue, where the methylene blue is taken as a dot here, and the photo degradation of the methylene blue over the titanium zirconic films, and for the both cases are observed. We can see that for the PMMA and pluronic F187 film, it is almost double times of efficiency compared to that of PMMA alone surfaces. Thus, we can conclude that we have prepared two types of films, which is amorphous in nature, TiO2, which is on the basis of PMMA, classified on the basis of PMMA, and also PMMA and pluronic F187. Both have very high thickness of micrometer ranges, and even though it is in the micrometer range, it shows high transmittance and also very highly retainable. And the self-cleaning retainability is due to the presence of the roughness of the film, which is provided by the presence of pluronic F187. So we observe the coatings with the transparency of 82% in the 300 to 600 nanometer and with the 2.7 micrometer thickness. And we acknowledge for the Emerging and Enable Materials Conference 2021 for giving me an opportunity to present this title. Thank you.
Good afternoon, I'm Ahmed Bagat, and in this poster I'm talking about study of the in vitro biodegradation behavior of magnesium zinc eggshell composite for orthopedic application. First, let me talk about some statistics of bone fracture. For example, in US, more than 100,000 fractures require treatment each year. In Qatar, more than 2,500 bone fractures have been estimated during 2014 and 2018 as a result of traffic accident. According to the head of orthopedic department in Al Ahli Hospital, 10,000 implants, including screws, plates, and wires and rods, were used in operation during the last 5 years. The most percentage of these implants were used in bone fracture surgery. 97% are permanent. Unfortunately, 47% required a second surgery to remove the permanent implant. So biomaterials alloy such as titanium, stainless steel are broadly used as implants. However, these metallic implants are much stiffer than natural bone due to the mismatch in modulus between the bone and the permanent implant. Stress shielding effect could accordingly happen where metallic parts are in contact with the bone, inducing bone resorption and decrease implant stability and finally failure. So magnesium alloys have been employed as biodegradable material due to their mechanical properties is relatively close to the natural bone and in order to avoid the second surgery. However, the main problem of magnesium alloy is their high corrosion rate, which can severely affect the mechanical properties and the integrity during tissue healing. The failure of the implants is in range of 70 to 89%. Crevice corrosion is the dominant degradation mode of failure with 86%. Therefore, the goal of this research is to evaluate the effect of the eggshell concentration on the corrosion performance of magnesium zinc eggshell alloys in simulated body fluid using different techniques and evaluate their cytotoxicity. The first figure illustrates the corrosion rate of magnesium substrate using the mass loss and hydrogen evolution measurement. Magnesium 2.5 zinc 3 eggshell showed the lowest corrosion rate. The biodegradation rate determined from the mass loss of the magnesium samples is consistent with the hydrogen evolution as shown in figure 1A and B. Figure 2 depicts the surface morphology of the magnesium samples after the weight loss experiment. The presence of microcrystal morphology in the corrosion product could be attributed to the dehydration after sample removal from the electrolyte. Figure 3 shows the presence of different morphologies, such as nanoflakes and needle-like structures, which were found in corrosion product in all of magnesium samples, which composed of calcium, magnesium, zinc, and phosphorus, as illustrated by the EDS mapping after immersion for 28 days in SPF solution, indicating the possible existence of magnesium and calcium phosphate in the corrosion product, which is the main composition of hydroxyapatite. The XRD and the FTIR were performed to explore the composition of corrosion products constructed on the surface of biodegradable magnesium samples. The diffraction peaks revealed that hexagonal magnesium hydroxide is dominant corrosion product. The FTIR spectra showed the presence of phosphate and carbonate signals, indicating formation of hydroxyapatite, which is thermodynamically more stable. The XPS of calcium and phosphorus confirmed the presence of hydroxyapatite, which is the scaffold for bone reconstruction as shown in figure 5. Figure 6 shows the surface morphology of magnesium samples after removing the corrosion product after 28 days of immersion in SPF. It can be observed that magnesium 2.5 zinc was significantly degraded with the presence of large and deep bits. However, the bit size significantly decreased in the presence of 3 eggshell. The electrochemical impedance spectroscopy showed that a 3 eggshell composition has the highest corrosion resistance as shown in figure 7. And in figure 8, the localized scanning vibrating electrode technique was done to assess the details of the microscale corrosion evolution, which confirmed that using 3 eggshell is the optimum concentration to resist corrosion. The cytotoxicity was evaluated in mouse embryonic fibroblast cells, indicating composition containing 3 eggshell is non-toxic, as shown in figure 9. Overall, magnesium 2.5 zinc 3 eggshell is showing the highest corrosion resistance and the lowest toxicity. The FTIR and XRD and XPS revealed the presence of hydroxyapatite, which is the scaffold for bone reconstruction, and accordingly, this alloy can be suitable to be evaluated in animals. At the end, I would like to express my grateful acknowledgement for the in-kind support that received from the Center for Advanced Materials. Thank you.
Have you asked yourself what our life would be without sun? We wouldn't have the solar energy we're using today as an alternative fuel cell. We all know that solar energy is clean and abundant, but when the sun isn't shining, we must store the energy in batteries or through a process called photocatalysis. In a photocatalytic water splitting, sunlight separates water into hydrogen and oxygen, which then can be recombined in a fuel cell to release energy. Howdy everyone, I'm Ghali Abdallah and my colleague Noura Sibairi. We're undergraduate research students from Texas A&M University at Qatar. Our research is supervised by Dr. Mohammed Al-Hashmi and Dr. Konstantinos Kakosimos. The focus of our research is on generating highly active and stable hydrogen gas using solar simulator device. while the main drawback that faces all solar utilities is the limited solar flux. And one of the main challenges we face is to identify an integrated material system that can perform all the different functions required of a photocatalyst. Our main objective is to assess the developed versatile strategy based on interfacing 2D nanosheets of existing semiconductor with 1D pi conjugated polymers. Different ratios of acceptor to donor were tested using different types of surfactants as shown in figure 2. The ratio with highest hydrogen evolution was obtained using solar simulator device that's shown in figure 3 and 5. Spin coating and drop casting were used to produce the film of our material as shown in figure 4. While the bandgap energy method was used to determine the bandgap energy of the nanoparticles, and other type of methods were used such as NMR, UV visible to identify and test the characteristics of the materials and surfactants that we were using. In collaboration with our national industrial partner, Qatar Shell Research and Technology Center, we were funded to conduct this project that achieves economic, human, environmental, and social development goals under Qatar National Vision 2030, and especially international goals such as the Sustainable Development Goal 11, Sustainable Cities and Communities, and 13, Climate Action, that are set by the United Nations. And as undergraduate researchers, working on this project had promoted interpersonal skills, which prepares us to become the next generation leaders through integrated research. And we were privileged to be trained in a multicultural training sessions by having on-campus and off-site visit, which reduces the impact of bias when we were working. This research project wasn't only funded by Shell, but also granted a funding by Qatar National Research Fund, which proves the important impact it will achieve in our community nationally and internationally. Now, my colleague Noura Al-Sabi'i will further discuss our achievements and the material synthesis.
Our research project was recognized and awarded first place internationally against participants from different countries, regions, and education level in the New Trends in Science and Technology International Conference, as you can see in figure 6. The theoretical synthesis was done to produce a small molecular acceptor and a donor polymer nanoparticles. And we have found that the donor has a higher molecular weight compared to the acceptor. Therefore, it can be observed that the donor polymer absorbed more light. Table 1 represents the bandgap energy of acceptor and donor with film and solution. The characteristic of the component with respect to wavelength is illustrated in figure 7. The nanoparticle solutions of different acceptor donor materials and composition were prepared to obtain the hydrogen evolution. The results are presented in table 2. We can conclude that regardless the acceptor or donor used, the optimum ratio is 10:90. We have also found that acceptor 1 and acceptor 3 produced the higher hydrogen evolution, which were around 3.7 and 3.6 micromole per hour. Yet, acceptor 2 also produced a maximum of 1.1 micromole per hour of hydrogen. The use of platinum as a co-catalyst showed a better performance in terms of the hydrogen production compared to the use of molybdenum. Also, the results shows that the use of nanoparticles suspended in the solution results in a higher hydrogen evolution rate compared to the use of the films. To conclude, the results demonstrate that the acceptor 1 over donor and acceptor 3 over donor systems composed of a 10:90 ratio provided the best results with a highest hydrogen evolution. This research project had acquired knowledge in impressively different fields such as material engineering, polymer chemistry, and analysis. Hence, it occupied us as an undergraduate chemical engineering students, researchers, with the rich resources of independences, persistence, sound judgment, and applicable industrial skills. Hope you enjoyed listening to our research project as much as we enjoyed working on it, and thank you for listening.
Howdy. The topic of today's poster presentation is hydrogen embrittlement in Inconel 718. Inconel 718 is a nickel-based alloy which is widely used in the oil and gas industries due to its high strength and corrosion resistance at temperatures up to 650 degrees Celsius. The Achilles heel of this alloy's use in the oil and gas industry is its susceptibility to hydrogen embrittlement, which affects its ductility and fracture toughness. An oil hose is shown here, the fasteners on which are made from a family of nickel alloys. These fasteners failed catastrophically and suddenly, and subsequent SEM analysis showed that they exhibited brittle, fracture, and secondary cracking, both of which are hallmarks of hydrogen embrittlement. In this study, we investigate the role of hardening precipitates that these alloys have on affecting its susceptibility to hydrogen embrittlement. So we create two versions of this alloy. One is solution treated, which has no hardening precipitates, while the other version is peak aged, in this temper there are hardening precipitates present, which also increase its hardness and strength. So the workflow of the study is shown here. We prepare samples using commercially procured 718. We EDM them into a typical tensile dog bone sample. Then we solution treat some of them, half of them to at 1100 degrees Celsius for 2 hours into the softer version, the solution treated version, and the other half is peak aged at 800 degrees Celsius for 8 hours. Then we prepare these samples, grinding and polishing, and then we charge them in an electrochemical cell. In this acidic medium, the hydrogen ions after the setup is polarized, all travel to the sample and form hydrogen gas, which can be seen bubbling at the surface here. Some of this hydrogen is taken up by these samples. Subsequent to the charging, we do some mechanical testing, and then finally we do post-fracture imaging. Firstly, we show the microstructure here of the solution treated temper. No precipitates can be seen here. However, after aging, their nanoprecipitates can be seen within the grains, and then we see some delta phase particles at the grain boundaries. These precipitates are responsible for increasing the hardness of this alloy from roughly 230 Vickers to almost 380 Vickers hardness. Interestingly, after charging in the solution treated temper, we observed a 20% increase in hardness. The same increase in hardness was conspicuously absent in the peak aged temper, where there was no increase in hardness after charging. Then we move on to some tensile tests at quasi-static slow strain rates of 10 to the negative fifth per second. Here we charge samples at two different charging current densities. The higher the charging current density, the more hydrogen is taken up by the sample. So the bottom three curves are for solution treated samples, and as we can see, the more hydrogen is in the sample, the higher is the loss of ductility, and the same trend is observed for the peak age samples. Loss of ductility is observed for both tempers at all charging current densities. However, in the peak age sample at the very high current density, we also observe a loss of strength, which is significant and is absent in all other cases. Subsequent to this tensile testing, we take some fractograph images. The face of the sample shows that was charged with hydrogen shows profuse secondary cracking. These secondary cracks, which did not propagate to failure, are absent in the uncharged samples. Looking at the cross section now, we see a very brittle layer close to the edge of the sample, whereas the interior of the sample has ductile dimple features. This shows that the brittleness is an effect of hydrogen, which bubbles at the surface and diffuses in, causing brittleness in regions close to the edge of the sample. The conclusions from the study are that firstly, the loss of ductility is there at all hydrogen at the two different hydrogen concentrations that we investigated. However, the increase in hardness is only there for the softer temper, while the drop in strength is only there for the peak age sample and at only the higher current density. Thus, there might be a critical hydrogen concentration, which is the subject of a future work where we will investigate at what concentration does the peak aged temper lose strength. We'll also investigate the role of tailored microstructures in affecting the susceptibility and eventually the resistance to hydrogen embrittlement of this alloy. Thank you for listening to my presentation.
Good morning. This is Shifa Sheikh. I'm a research assistant at the Center of Advanced Materials at Qatar University. The current project is aimed at fabricating and testing of block copolymer membranes in treating oily wastewaters. As is fairly known, oil and gas operations generate large volumes of produced water, which is essentially wastewaters primarily characterized by high concentrations of hydrocarbons, apart from other pollutants. The beneficial reuse of the produced water requires intensive treatment, for which membrane separation technologies are deemed suitable, among a range of other technologies. In this project, we fabricated a special class of thin film composite membranes for this application using block copolymers. Block copolymers, or BCPs, consist of two chemically incompatible polymers that are covalently linked at one end. This is a novel class of polymers that can self-assemble into uniform, chemically distinct microdomains, resulting from intermolecular phase separation. The sizes of these microdomains range from 3 to 50 nanometers. As a result, these membranes have a well-ordered nanostructure, offering high selectivity, low tortuosity, excellent oil separation efficiency, and reduced fouling tendencies. As seen in the figures on the left, an ordered BCP layer is generally incorporated into porous membranes to form composite membranes. These comprise of a selective thin film BCP layer with a thickness usually exceeding 80 nanometers, which is coated on a thick layer of macroporous material of approximately 100 micrometers thickness that serves as a mechanical support. Among the various annealing processes employed for polymer films, this project focuses on the non-volatile additive solvent annealing method. In this method, the BCP layer is simultaneously deposited and ordered while fabricating the composite membrane. This is a two-step process which involves the introduction of a high boiling point solvent to a BCP solution of a low boiling point solvent. Once the solution is coated, the host solvent quickly evaporates, while the high boiling point solvent remains, swells the BCP membrane, and gradually evaporates. The swollen state of the film increases the BCP chain mobility and facilitates increased order within the BCP film. The figures on the right exhibit the top surface of the thin film BCP layers ordered by different annealing methods. They are generally characterized by well-ordered, vertically oriented nanopores. In comparison to the other methods, non-volatile solvent annealing method is simple, rapid, energy efficient, and cost-effective. These advantages provide opportunities for this technique to be incorporated into large-scale manufacturing processes. Finally, filtration tests were performed for the membranes to test their oil separation efficiency using synthetic oil-water tight emulsions. A stirred filtration cell in a bench scale setup was applied for the purpose. The specific flux of the membrane was monitored, and the TOC rejection was measured for the permeate to determine the membrane performance. For instance, one of the BCP membranes prepared by solvent annealing method, a steady decline in the specific flux was observed over 4 consecutive filtration runs. However, a high TOC rejection was also recorded for the permeates of the 4 runs, all of them exceeding 90%. The results emphasize the high selectivity of the membranes, high resistance to fouling over multiple runs, and their excellent oil separation efficiencies from wastewaters. In future, the membrane performance will also be evaluated for real field produced water samples procured from an oil and gas company in Qatar. Thank you very much.
Hello everyone. Imagine life without mobile phones, televisions, and various modern optoelectronic devices that have become an essential part of our lives. These devices have become a reality because of conducting materials that have emerged in the last 50 years. When we think of materials that conduct electricity, we usually think of metals, not of synthetic organic polymers such as plastics. Recent research has demonstrated conducting and semiconducting properties of the conjugated polymers. These polymers have emerged as efficient materials for electronic applications and have helped to open an era of plastic electronics. A Nobel Prize in Chemistry was awarded to the inventors Professor Higa, Professor McDermott, and Professor Shirakawa. Today, semiconductor polymers find applications in light-emitting diodes, field effect transistors, and photovoltaic solar cells. With the understanding of chemical design principles, charge transport physics, the field of conjugated polymers is marching into next generation applications such as wearable soft electronics and energy storage devices, as well as photocatalytic fuel generation. My name is Salahuddin Attar. I'm working as a postdoctoral research associate with Professor Muhammad Al-Hashimi on a QNRF-funded project at Texas A&M University at Qatar. I will present some of my work on conjugated polymers entitled thiazole fused SN heteroacene step ladder polymeric semiconductors. Different aromatic heterocycles containing sulfur nitrogen, namely thiophene, pyrrole, thiazole, pyridine, etc., when fused together, form a pi conjugated system called SN heteroacene. They resemble ladder due to their apparent conformation. Herein we have synthesized 3, 6, and 9 ring fused SN6, SN6, SN3, and SN9 thiazole monomers. And these ladder monomers have electron donating unit, the electron rich thiophene and pyrrole rings, and electron accepting unit as thiazole rings fused at the terminals. The monomers are synthesized following 3 main steps: the palladium catalyzed Buchwald coupling of monobrominated precursors with straight and branched alkyl amines to achieve cyclization, forming a fused pyrrole rings. This was followed by the protection of triisopropyl groups at the ends using tetrabutyl ammonium fluoride, and finally brominating using N-bromosuccinamide to obtain monomers ready for polymerization. The homopolymerization was achieved by reacting dibrominated monomers using palladium catalyzed Steely coupling reaction, whereas copolymers were obtained by reacting stanylated thiophene diketopyrrolopyrrole. These reactions gave distinct blue color for homopolymers and green color for the copolymers. All the precursors and monomers were characterized by proton and carbon nucleomagnetic resonance spectroscopies. Some of the precursors were crystallized, and single crystal X-ray diffraction studies were confirmed their structures, as depicted in the animations. Crystal structures of the ladder monomer, SN6 thiazole ladder monomer, form an end-to-end bypass stacking necessary for intermolecular charge transfer in the solid state. This is clearly displayed in the crystal packing mode of SN6 thiazole ladder. There occur distinct difference in absorbance of SN6, SN9 thiazole ladder monomers, the former showing blue emission while the latter showing the green emission when excited in 365 nanometer light. This happens due to the extended pi conjugation from 6 to 9 rings. Both homopolymers with blue color strongly absorb in visible region ranging from 400 nanometer to 800 nanometer, while with a slight redshift in the solid state absorbance. The copolymer also absorbs from visible to near infrared region. Cyclic voltammetry was performed on thin films of polymers to obtain their molecular orbital energy levels. The graph shows a well-defined oxidation reduction waves. Band gap is lowered with extended conjugation is achieved by polymerization. Copolymer has a smaller band gap than a homopolymer due to the facile electron transfer from the donor ladder unit to the acceptor DPP unit. Density functional theory calculations were performed to obtain molecular orbital and the band gaps. Atomic force microscopy was performed on the thin films of the polymers to observe the physical behavior in the solid state. Finally, charge transport characteristic was carried out by our collaborator, Professor Yao Liu. All the polymers based OFID devices exhibited annealing temperature-dependent performance, with the copolymer exhibiting highest mobility of 0.05 centimeters square per volt second. In conclusion, these are novel materials prepared from start to end in Qatar while analyzed in China. These novel materials are promising optoelectronic properties and are worth exploring further in different fronts. Lastly, I thank QNR for funding this project and thank you all for your kind attention.
Hello everyone, this is Muhammad Rabia from Qatar University. I'm a research assistant at the Center for Advanced Material, and today I am going to share with you my poster for the Emerging and Enabling Material online conference. Today, I'm going to present to you one of the topics of the research about development of sustainable eco-friendly geopolymer composites for construction applications. To introduce you to the topic, geopolymerization is a process where source materials that are rich in silica and aluminum is used with alkaline solution to produce geopolymer mortars, which that's why it's called alkali activation, because it uses alkali solution. Fly ash is the main resource used to bind these material. Fly ash is the source material used, as I mentioned. Also, sodium silicate and sodium hydroxide alkali solution is used to produce sand in order to produce high strength geopolymer construction mortar. It can be used for applications such as repairing concrete existing structure, old structure. So in this study, we developed a parametric study to investigate the feasibility of using alkali activated mortar in the applications for construction. We evaluated that based on the mechanical strength and also the flexural strength. The results that, in conclusion, the results that showed very high early compressive strength, reaching to 63.9 megapascal for samples that were cured at 80 degrees, and that's only after 24 hours of curing. The objective is to investigate the factors influencing the mechanical properties of geopolymer mortar and what are the best practices and optimum conditions. The objective to produce geopolymer binder is that it's innovative construction product. It can reduce the waste. Also, it reduces the carbon footprint. Why this research is significant is that it allows to establish methods for high strength of geopolymer mortar that can be used in civil engineering applications. Also, the second thing about the significance is that it can reduce the environmental impact of the construction industry due to the use of traditional construction material and using source material that are not pollutant to the environment. So it's cement-free, environmental friendly construction material. It doesn't need water, so no water at all, and it produces strength with superior mechanical strength. Our motivation for this research is that because cement production requires immense amount of energy and it's accountable for 7% carbon dioxide emissions to the atmosphere, it's estimated that 1 ton of producing cement is equal to 1 ton of carbon dioxide, which is a very huge number in terms of the environmental impact. And there has been an increasing demand to find a solution and to find an alternative, more eco-friendly construction material, and that's where alkali activated materials comes into place. So the sustainable geopolymer concrete, it's durable, it needs less maintenance, it's recyclable, needs less energy, and uses less natural resources. So to present you what are the methods and materials that we used, the materials we use: sand, fly ash class F, activator solution, sodium hydroxide and sodium silicate with different concentrations. The methods is that we prepared, we followed the procedure according to the ASTM standard for producing mortar. And as you can see here, we prepared the alkali activated mortar, the geopolymer, and then we placed it in the oven for curing. The curing duration was variables that we included in the study: temperature, duration, and age of mortar. So moving on to the results, the result shows that the effect of sodium hydroxide solution and sodium silicate to sodium hydroxide ratio is that the higher the molarity of the sodium hydroxide solution of 16 molar exhibited the highest compressive strength. That's for all sodium hydroxide to sodium silicate to sodium hydroxide ratios. And we reached the minimum compressive strength of 33.4 megapascal for geopolymer with 12 molars of concentration of sodium hydroxide, as can be seen here from figure 6. So the reason is that is the higher the concentration of sodium hydroxide, the higher alkalinity, it increases its ability to react with the materials and form the geopolymerization products and the geopolymer gel that binds the materials together. Also, as we increase the fluid to binder ratio, there was some variation in the compressive strength. We reached the minimum compressive strength of 45 megapascal with 14 molar of sodium hydroxide, which can be illustrated here from the graph that shows here. And moving on to the effect of curing conditions, we studied 3 different temperatures for curing, and we noticed that if we have lower temperature of curing, the samples are not cured well and it does not produce high compressive strength. But we find the optimum curing temperature that was 80, which exhibited the highest compressive strength between all. Once we increased the curing temperature to the 120 degrees, it adversely affected the strength, the mechanical strength. And now we wanted to study the scanning electron, the microstructure of the material itself. So it gives us an indication of how the materials are reacted. As we can see here, the effect of the molarity of the sodium hydroxide solution has been clearly observed with the scanning electron microscopy. In addition to the higher the molarity, it shows here the better matrix that's developed. The amount of reacted fly ash particle increased as well. So let's see these figures. So as we can see here is the geopolymer matrix, and those are unreacted fly ash particles, and we can see here cracks and some voids. With moving on to higher molarity, we can see a more developed matrix with more reacted fly ash particles and some unreacted fly ash particles. And also, the higher we increase the sodium hydroxide solution concentration to 16 molar, we found out that almost all fly ash particles were reacted with the solution, and the binding and the dense geopolymer matrix was developed. So in conclusion of this research, it proves that we can use geopolymer mortar to replace cement mortar in civil engineering application. The application that can be used is that for repair material. It can be used as repair material. The findings of this research was that we found that the higher the molarity, the better the compressive strength for the geopolymer mortar. The effect of fluid to binder ratio is a major contributor to the mechanical strength. We can achieve a maximum yield strength of 63 megapascal, with sodium hydroxide solution concentration of 16 molar and fluid to binder ratio of 0.6, sodium silicate to sodium hydroxide ratio of 1. Also, heat curing is preferable to reach better compressive strength and early and better compressive strength. Geopolymer strength gains strength with age. Geopolymer mortar gains strength with age for both heat curing and room temperature curing with different levels of or with different rates for gaining the strength. Fly ash made of sodium hydroxide only has very low compressive strength compared to this made of both sodium hydroxide and sodium silicate, which is confirmed by the SEM results, as you can see here. So I would like personally to thank the support of Qatar University Graduate Studies Office and the Center for Advanced Material that made this research possible. And thank you so much. It's a pleasure to work at the Center for Advanced Material, being a researcher here for almost 3 years. It's a pleasure for me. I learned a lot I gained a lot of research experience with multiple publications, thanks to my supervisors, Dr. Muhammad and Dr. Nasser. And I hope you find this poster helpful and informative. Thank you so much.
Hello everyone, my name is Manaf Degoed, a PhD student in mechanical engineering from Texas A&M University, and I'm here to share with you my research on microstructure engineering of ZK40 magnesium alloy for biodegradable orthopedic applications. Now, the motivation between my research is that it has been reported that there are 2.2 million bone grafting surgeries that are performed worldwide each year. Unfortunately, most of these surgeries require secondary removal surgeries because they involve permanent implants. And there are risks associated with the surgery, such as post-surgery complications, for example, inflammation and toxicity. There's high risk when you're dealing with children and elderly patients, and the process itself is expensive. And that is why there has been a shift towards biodegradable orthopedic implants. Now, there are specific design criteria for these implants. They should have appropriate mechanical properties so that they can temporarily support the bone while it's healing. They should have suitable corrosion resistance to allow for progressive degradation, and the implant does not degrade too fast before the healing has been completed. And finally, they should be compatible so that when the metal is degrading, it's releasing ions, and we need to make sure that these ions are not toxic to the human body. And that is why magnesium and its alloys have gained wide attention within this realm, because of the fact that magnesium is already found in the body, it's found in bones, soft tissues, and it's involved in several cellular functions, such as protein synthesis. Magnesium also has a high daily intake that can be withstood by the human body, and it was found that its alloys had physical and mechanical properties that are very close to the human cortical bone. And as you can see here from this research, that when a magnesium-based implant was used, there was better bone growth and osseointegration compared to a polymer implant. Now, unfortunately, when we compare magnesium-based alloys with other metallic-based implants, such as iron or zinc, we find that they have high degradation rates, and so work is needed to be able to control their degradation rates. Now, in my research, I focused on magnesium zinc zirconium alloys, or ZK alloys, because when compared with other magnesium alloy families, they were found to have high strength, good corrosion resistance, and biocompatible, because of the two other alloying elements, zinc and zirconium, are also found within the body. Now, to manipulate the microstructure, I used a severe plastic deformation process called equal channel angular pressing, or ECAP for short, where the alloy is pressed through a 90-degree channel, and the resulting strains causes grain refinement. Now, this allows me to modify the corrosion kinetics without changing the composition of my alloy. And it was found that the corrosion resistance actually increased with the refined grains because of a more coherent and stable film forming on the alloy due to the increased number density of dislocations as well as the high misorientation angle of grain boundaries. So looking at the results, we see here the microstructure for ZK40 where a heat treatment was done to try to dissolve these dark streaks of secondary phases. And the second microstructure is for the ECAP process where we find that definitely there is a significant refinement of the grains and a more homogeneous structure than what was found with the heat treatment. Now, electrochemical results, on the other hand, showed interesting degradation rates where it was found that the polarization resistance and the double layer capacitance both resulted in an increased degradation rate after ECAP. Now, this is different to what we expected, and that led us to look into the surface film. So here we have SEM images of the cross-section areas of both alloys, and we find that in ZK40 heat treated, there was a much thicker and much more a coherent film formed than the ECAPed alloy, where it had a thinner film and the film had was starting to disintegrate. We also found by EDS analysis that this film was actually mainly zirconium oxide, and from other research it was found that actually zirconium oxide was used as coatings on magnesium alloys to improve their resistance. And so our explanation for that is that while ECAP has indeed refined the grain, it has also refined or disintegrated the secondary phases, which increased the microgalvanic corrosion between the secondary phases and the matrix, and so that led to a increased corrosion rate and a less stable and a weak and thinner surface film. And so in summary, ECAP did result in a homogeneous microstructure with significant grain refinement, but also led to disintegration of secondary phases. And this disintegration resulted in a decrease in the polarization resistance and an increase in double layer capacitance, which therefore accelerated the corrosion behavior of ZK40 post ECAP, and which therefore produced a less stable zirconium-rich surface film that did not contribute sufficiently to the corrosion resistance of ZK40. Thank you so much for listening, and I also thank you, QNRF, for supporting this research.
Hi everyone, I'm Stephanie. I'm from Mexico, and the topic of my poster is Analysis of the Thermal Stabilization of Precursor Fibers Synthesized from a Suspension Polymerization Process. As introduction of this study, the stabilization of the precursor fibers is one of the most important stages in the production of carbon microfibers. The stabilization conditions, such as time and temperature, are critical to guarantee their high quality. For this work, a study of the thermal stabilization of acrylic fibers obtained from a suspension polymerization process was carried out, such as the one shown in Figure 1. For example, one advantage of this process is that the reaction of the monomer is made in aqueous medium, therefore the stage of recovery and treatment of the polymer for its subsequent use are minimal and economical. Regarding to the methodology, in the Figure 2 shows a general procedure for obtaining and thermal stabilization of precursor fibers. For example, for stage 1, the control factors and levels of the design experiments were established. 12 tests were obtained from 11 factors with 2 levels. In the table 1 shows the factors and experimental conditions, such as the type of monomer, factor E, its concentration, factor B, the thermonomer, factor C, itaconic acid for level 1, and boric acid for level 2, and so on. The evaluation of the design data was carried out by analysis of variance. Otherwise, the other stages of methodology are synthesis of acrylic polymers, production of precursor fibers by wet spinning and their thermal stabilization, and finally, their characterization by infrared spectroscopy techniques, scanning electron, microscope, etc. Results. In total, 12 polymerization reactions were carried out. In Table 2, the result of the characterization of polymers produced are shown. For example, the percentage of conversation obtained is in the range 28 to 72. In the figure 3, you can see a sample of polymer obtained by suspension polymerization. By another way, the ANOVA of determined stabilization index terpolymers determines oxidation of the polymers was determined by infrared spectroscopy, FTIR, and the stabilization index. According to the ANOVA, Table 3, when the p-value is less than 0.05, the factors that have a significant impact on the stabilization index. The comonomer and the thermonomer, specifically acid taconic units, improve the stabilization index of the polymers. On the other hand, the use of acid boric produces a retarding effect. In the figure 4, shows the FTIR of the polymer 1 composed of the monomers acrylonitrile, methylacrylate, and itaconic acid. The FTIR of the green line is the acrylic polymer, and the green line is the oxide polymer, and this stabilization index is 2.74. The cyclation reaction transforms the nitrile groups into cyclic groups, as shown by the gradual decrease of the peak to 2240. Thermal stabilization of precursor fibers. Regarding thermo-oxidized fibers, M4, their stabilization index is 5.68 and their tensile strength value is around 500 megapascals. That is, they are classified as high modulus fibers. So the M4 filaments, figure 6, have similar dimensions. The surface has little damage and is raw, which can be associated with high molecular weight and consequently high mechanical resistance. As a general conclusion, acrylic polymers obtained by suspension polymerization show high conversion percentage and also high molecular weight values, which is why they are considered useful for the production of precursor fibers for the industrial application. However, the use of the highly straight acrylic fibers don't guarantee obtaining high modulus carbon microfibers. Therefore, the correct time and temperature must be used for the thermal stabilization of precursor fibers. Also, the consulted references are shown. Finally, thanks to Qatar University for the invitation to the conference Emerging and Enabling Materials, and Instituto Technology Aguascalientes for supporting this research project.
Hi, my name is Daniela Quiroz, and today I'm going to present to you our project about the effect of HBN exfoliation method on the barrier and corrosion inhibition of the epoxy HBN nanocomposite coatings. New material with enhanced corrosion protection are needed to reduce maintenance costs and increase the lifespan of the structures. It is worth noting to point out that the best corrosion protection strategy is not only the one that provides the highest innovation performance, but also the cost-efficient, easy-handled, and of course, less polluting process. The addition of 2D nanosheets of hexagonal boron nitride has proven to provide outstanding long-term corrosion protection as nanofillers into polymeric coatings. As you can observe in the image of the HBN sheet-like geometry increases the corrosive species touristic path, improving the corrosion protection efficiency of the coatings. These nanosheets can be synthesized by either mechanical exfoliation methods such as ball milling or liquid exfoliation. Previous studies fabricate optimal coatings employing one of these techniques, but there is no comparison between them so far. In this work, epoxy HBN nanocomposite coatings are prepared with both methods. The effect of HBN loading and exfoliation method on the barrier corrosion properties are investigated. Experimental procedure includes initially the nanosheet synthesis via both methods. The fillers are dispersed into the epoxy matrix and coatings are fabricated. The characterization of the powders to prove the exfoliation of the nanosheets were made, and finally the coatings undergo electrochemical testing, that is open circuit potential and electrochemical impedance spectroscopy, to measure the anti-corrosion performance. For both methods, the SEM image show a clear reduction in the lateral size and thickness of the particles. The ball mill powder show more defects and a smaller average particle size compared to the liquid exfoliation. The surface area analysis results show an increase in the surface area after both exfoliation methods. Ball milling has the highest surface area, and XR depict the 0.02 broadened, decrease, and shift to the left. This is a sign of exfoliation. All mill samples expose around 10 layers less than the liquid exfoliation sample. All composite samples show more positive OCP compared to the neat epoxy and the pristine 0.25 that were used as a control sample. The most stable and protective coatings are the liquid exfoliation 0.25 and the ball milling 0.25 due to the homogeneous distribution on the epoxy matrix. As we increase the loading percentage, the protection is reversed due to the particle agglomeration. The fluctuation on the OCP values are related to the mixed response of the different reactions that are taking place at the metal coating interface. When rust layer is formed, the potential could be shifted toward more electropositive values due to the noble potential of oxides. However, iron oxides are not stable or compact, so eventually the potential drops down again to more electronegative value, resulting in the failure of the barrier property of the coating and formation of the corrosion products. Nyquist and both plots are exposed in this side of the slide. The diameters of the impedance are a low frequency of the neat epoxy and pristine sulfur start shrinking after 18 days of immersion time, which indicates the continued decline of the barrier effect supplied by the coatings and decrease in the charge transfer resistance. The ball milling 0.25 and liquid exfoliation 0.25 diameter expose an increasing trend over time. The phase angle plots show the two-time constant appearing after 36 and 42 days for the neat epoxy and the pristine respectively. However, in the case of the ball milling and the liquid exfoliation, only one-time constant is observed during the entire immersion time. Now, in the left side, the screen, the variation of the impedance modulus at the lowest frequency is observed. From the figure, it can be concluded that the magnitude of the neat epoxy and the pristine sample is lower and decrease faster compared to the composite coatings. However, for the liquid exfoliation 0.25 and ball milling 0.25, the impedance modulus magnitude expose an increasing trend over time and are very similar. As mentioned before, the formation of the rust layer could delay the corrosion process, increasing the charge transfer resistance. This scenario is the same for all coatings. However, based on the results, the stability of the rust layer of the liquid exfoliation and ball milling seem to be larger than the neat epoxy and the pristine, since the electrolyte permeation depends on the nature and the distribution of the fillers into the matrix. In the case of the ball milling and the liquid exfoliation samples, the nanosheets distribution at 0.25% of nanosheets is homogeneous, so the concentration of the electrolyte that permeates the coating is lower compared to the control samples, so the probability to produce localized corrosion is also lower. In contrast, the high concentration of electrolyte in the control samples promotes localized corrosion due to the heterogeneity of the barrier due to the defects and the agglomeration of the filler. The mechanism can be observed in the left side of the screen. So for the conclusion, electrochemical studies show that the inclusion of the 0.25% of fillers synthesized via both methods results in excellent corrosion inhibiting coatings outperforming neat and pristine HPN. Since both methods pose no significant difference in their anti-corrosion performance, ball milling should be the best option, the best process, because it's easier to operate on an industrial scale, unlike the liquid exfoliation that requires a very long period of time to process and has a very low nanosheet